Look up at a passenger jet on final approach. The engines hang beneath the wings, slung low in smooth pods called nacelles. A nacelle is the streamlined casing that wraps around an engine and holds it to the aircraft. It looks almost careless. Two enormous machines, each weighing several tons, dangling in open air below the very surface that keeps the plane flying. Why put them there? Why not tuck them into the fuselage, the main body of the aircraft where passengers sit? Why not bolt them to the tail or bury them inside the wing itself? Every choice on an airliner is fought over by engineers for years. Nothing hangs by accident. The Boeing 737, first flown in 1967, carries its engines under the wing. So does the Airbus A320. So do the giants, the Boeing 747 and the Airbus A380. These are the most successful aircraft ever built, tens of thousands of them, and nearly all of them share this same strange silhouette, engines below the wing, forward of the leading edge. That consistency is a clue. When the entire industry converges on one answer across 60 years and countless designs, something deep is driving the decision. The reasons touch physics, weight, noise, and the simple problem of a mechanic needing to reach a broken part on a cold morning. And there is a hidden tension inside the design. The very position that solves so many problems also creates one that engineers still wrestle with today. To understand why the engines hang where they do, we have to start with the invisible force holding the whole plane up. The strangest part was still coming. A wing does not simply push against the air. As it moves forward, the curved upper surface speeds the airflow, lowering its pressure. Higher pressure below, lower pressure above. That difference is lift, the upward force that carries the aircraft. Lift is not spread evenly. It concentrates along a region of the wing called the center of lift, the single point where all that upward force effectively acts. Now think about weight. An engine is dense and heavy. A modern turbofan, the type of jet engine that uses a large front fan to move air, can weigh more than 6 tons. Where you place that weight matters enormously. Put it far from the center of lift, and the wing must fight a twisting load, bending and straining across its length. But place the engine close to the center of lift, forward and below the wing, and something elegant happens. The weight sits almost directly under the force lifting it. The wing carries the engine the way an open hand carries a stone resting on the palm. There is more. In flight, lift pushes the wings upward while the heavy fuel and engines pull them down. These forces partly cancel. That balance reduces the bending stress at the wing root, where the wing meets the fuselage. Engineers call this bending relief. It lets them build lighter wings. Lighter wings mean less fuel burned, more range, cheaper flights. So the hanging engine is not dead weight in the wrong place. It is a counterweight, working with the wing rather than against it. That is the physics. But physics alone does not explain everything. There was a reason mechanics and passengers came to love this layout too. An engine is the part of an aircraft most likely to need attention. It runs hotter than a furnace, spins faster than almost any machine humans build, and swallows enormous volumes of air every second. So it must be inspected constantly, serviced, repaired, sometimes swapped out entirely. Now imagine reaching that engine. If it hangs low beneath the wing, a mechanic can stand on the ground, roll a work stand into place, and open the nacelle cowlings, the hinged panels that fold outward like the hood of a car. The whole engine is right there at working height. It can even be lowered and replaced in hours rather than days. On a busy airline, that time is money, measured in thousands of dollars per hour on the ground. Compare that to an engine buried in the tail or inside the fuselage. Reaching it means scaffolding, awkward angles, and far more labor. The underwing position also helps passengers, though most never notice. The engines sit below and behind the leading edge, ahead of the cabin. The wing itself becomes a barrier, blocking some of the roar from reaching the seats. And there is safety in the arrangement. If an engine ever suffers an uncontained failure, throwing debris outward, the position and angle help direct that danger away from the fuselage and the people inside. So the layout wins on three fronts at once: the physics of lift, the ease of maintenance, and the comfort and safety of everyone aboard. It sounds like the perfect solution, but every engineer looking at that low-hanging engine sees the same problem staring back at them. And that problem nearly reshaped the modern jet. Here's the trouble. The engine hangs low, the ground is right there. The distance between the bottom of the engine and the runway is called ground clearance. Too little of it, and the engine can strike the tarmac during a hard landing, or ingest debris, or scrape on takeoff. This was a small issue in the 1960s, when jet engines were narrow. But engines grew. To burn less fuel, designers made the front fan wider and wider, moving huge volumes of air more gently. A bigger fan is more efficient. It is also physically larger. The Boeing 737 shows the strain most vividly. Its original engines were slim, but newer, fatter engines would not fit under its famously low wing. So Boeing engineers did something clever. On the 737 Next Generation, launched in the 1990s, they flattened the bottom of the nacelle, giving it a distinctive, squashed, non-circular shape. It looks almost like a pinched oval. That reshaping bought precious inches of clearance without redesigning the whole aircraft. Other designers took different paths. Some raised the wing higher on the fuselage. Some, on smaller regional jets, gave up entirely and mounted the engines on the rear of the fuselage, accepting the maintenance and weight penalties. And some, like the Airbus A320neo, simply designed taller landing gear to lift the whole aircraft and make room for larger engines. Every solution is a compromise, clearance traded against weight, against drag, against cost. The hanging engine, so perfect on paper, forces engineers into a lifelong negotiation with the ground beneath it. Which brings us to what all of this really means the next time you board a plane. The next time you walk down a jet bridge, glance out the window at the wing. That engine hanging below it is not an afterthought. It is the visible answer to 100 hidden questions. It sits there because the wing above it is the strongest, most efficient place to carry heavy weight. The lift and the load meet almost in the same spot, and the wing barely notices the burden. It sits there because a mechanic on the ground can open it like a car hood and fix it in hours, keeping the aircraft flying and tickets affordable. It sits there because the wing shields your ears from the worst of the noise, and because its angle helps protect you if anything ever goes wrong inside. And its exact shape, whether round or flattened, whether high or low, tells a story of the endless fight for clearance above the runway. So the silhouette you have seen your whole life, the shape you would draw if someone asked you to sketch an airplane, is not arbitrary at all. Every line of it is the settled outcome of decades of argument between physicists, mechanics, accountants, and safety engineers. The plane looks the way it does because the numbers demanded it. That dangling engine is the most elegant compromise in modern aviation, hidden in plain sight above the tarmac. You will never look at a wing the same way again. What seemed careless is actually the most carefully balanced decision on the entire aircraft. The engines hang beneath the wings, because that is exactly where physics, safety, and cost all agree.